Good afternoon, and thank you everyone for coming this afternoon. I'm Sean, and I represent SmartAIR Diffusion. Some of you will know the company under its previous name, which was Crunch Asia Pacific. Of course, we no longer represent Crunch products. What we do represent is our own brand, SmartTEMP, which is what I'm going to be concentrating on today, as well as LTG from Germany, and Harmony, which is also one of our brands. But this is the range of premium products that we've been developing over the years, and which I want to talk about in particular. The company's, and certainly my experience with air diffusion in this part of the world goes back to 1995, when we originally brought Crunch Air Diffusion to New Zealand, and then later in 2001 to Australia after I'd worked at Crunch in Germany. And during this whole time, the idea was to bring the German technology of high induction mixed flow air diffusion and energy efficient concepts over here. But it also gradually became apparent to us that as much as these diffusers work well in Germany, that this is not Germany. There are distinct differences over here. We've got higher airflow rates. We generally have different heat loads. We do a lot of heating through the air side, whereas Germans use radiators. So substantial differences, which of course mean that you cannot just take the products as they are in Europe and expect them to perform over here. And as a result of that, we started developing products together with Crunch initially, specifically for our part of the world. And in about 2005, 2006, we launched what was called the Crunch REN3 Swirl Diffuser, which is in fact this diffuser right over here, now sold as the Harmony diffuser. So I co-developed that product with Dr. Zordich, and that was a high volume swirl diffuser developed specifically for the Asia Pacific region and for the Green Star wave that was coming, the 5 Green Star low temperature VAV buildings that then happened in Australia in particular. And then following on from that, we took those concepts further with other types of diffusers, which we developed, and some of those diffusers you'll see today as I go through the presentation. We then separated ways from Crunch in 2015, when Crunch decided, we had, I should say prior to that, we were manufacturing products under license to Crunch in our factory. This is our factory in China. It's not a third-party factory. It belongs 100% to us. But in 2015, Crunch in Germany made the decision that all products worldwide had to be sourced from Germany. And that just wasn't a viable business model for this part of the world. And so we split from Crunch, and as I said, we've been developing products, many of which were being sold under the Crunch brand anyway, but belonged to us. And so we took those with us and have carried on with a lot of R&D since then, which you'll see in the next slide. But that gives you a little bit of a background, and we've also started a partnership, as it were, with LTG in Germany, which is a Stuttgart-based company, and we do quite a bit of our testing in their laboratories over there. They represent us and we represent them. But this is our laboratory in Sydney. We've got a few. We've got the demo lab, we've also got a high lab and a general lab, and we do a lot of product development there. The lab is busy all the time. We will be launching a new range of products next year, which I'm not able to talk about now. That'll be a completely different presentation, and that's what's happening right now in the lab. The lab is not only used for our product development, it's also used for project-specific tests. This is an example for the Sydney Opera House, for example, where you can see this is the new function centres that have opened. You can just make out the harbour bridge. There's this curved concrete beam over here with air diffusion above that, which then has to deal with this facade area. Here you can see the idea. The linears, the concrete beam, and the facade, which we had to mock up with a heated wall and false concrete beam and the air diffusion over there. Because the air magically had to get through this concrete somehow to deal with the glazing. And we've done quite a few tests also for Star City Casino and so forth. So that's something we can do for New Zealand as well. If there are projects that require a bespoke solution, we are absolutely able to do testing and fine-tuning. So today's presentation is going to concentrate on mixed flow. I normally talk about displacement as well, but due to time constraints, I'm going to keep it purely to the mixed flow side. But I've always found that these two beakers represent the two concepts rather well. Over here on the left, we've got a guy sitting in contaminated water representing the heat and the contaminants that we have in the space, carbon dioxide, formaldehydes, or off-gassing from cleaning materials or whatever, and then that being diluted by the fresh, cool water in this instance, coming in, mixing with it, and then those heat and contaminants are removed by dilution. As opposed to the concept of displacement, where we do the opposite. We don't want mixing. We instead want to very gently purge, like a piston, the heat and contaminants upwards so as to cocoon the occupant in the higher indoor air quality. But I will not be talking about this today. I'll be talking about the left-hand side. And when it comes to mixed flow, most of us are familiar with this. This is what I call the American concept of mixed flow. I'm showing it because this, in a sense, is actually what we do not do. Certainly not in terms of the European concept. But what the American concept is that we have cold air that we're supplying into the room. That air is dense, it therefore wants to fall down, and that's going to create a draft. We don't want that draft, and so what we typically do is we discharge the air at a relatively high velocity across the ceiling. That creates Coanda effect attachment, and the air then spreads, and all our problems are meant to be solved. But they're not solved, because when the cold air hits a wall, it's deflected down, it creates a draft over here where two air streams clash, we get a draft. Or if we get rid of this diffuser on the left, and the air over here is meant to get all the way to the left, it slows down, it detaches, it also creates a draft. And so it's not really the silver bullet that it's meant to be. Now the European approach to mixed airflow is a little different. They've said the reason that we've got this issue with draft is because the air is cold and heavy and wants to fall down. So let's stop it from being cold and heavy. Let's have a high induction diffuser that draws in lots of room air and mixes it into the supply air stream, substantially equalizing the temperature of the supply air with the room air, which means it's effectively the same density. And that means it doesn't want to drop down in the first place. So that's the basic concept, but there's a bit more that happens, because as all of this room air is drawn into the supply air stream, the mass flow rate over here increases. It's all the primary air plus lots of secondary air coming in, so we get this huge increase in the air flow. Now energy can't be created or destroyed, we know that as engineers, so if mass flow is going up, something's got to go down, and that something is velocity. It's just a simple transfer of energy. And so within a very short distance of the diffuser, we've got this big mass flow rate of air traveling very slowly and at substantially the same temperature as the room air. So that's great. When these two air streams clash, the temperature is almost the same, the velocity is almost the same, so the risk of draft, or the velocity is very low, I should say, and so the risk of draft is hugely reduced. So that's good, and it certainly means that these diffusers can be close to walls, can deal with high heat load situations, but what if we want a long throw? What if we get rid of this diffuser over here, and we want this air to go all the way across there? And I'm usually told, well, obviously, this sort of diffuser is not going to be able to deal with that. The velocity is low, so the throw must be short. But it's not true, because throw is not a function of velocity. It's actually a function of momentum, and momentum is mass flow rate times velocity. The very reason that the velocity has gone down over here is because the mass flow rate's gone up. It's just a transfer of energy. And so yes, this air is moving slowly, but it's a big mass of air, and it keeps on moving over a long distance, just like a billiard ball. It might be rolling slowly, but it's heavy, and it keeps on rolling. And that's what happens with high induction diffusers. And so they're very forgiving diffusers. They're very good for short throws and for long throws as well, which means that they're very good in VAV applications. And it brings me back to what I was saying right at the beginning with the what was then the Kranz-Orient 3, now the Harmony, is that it was actually developed as a VAV diffuser for low temperature VAV applications in 5 green star rated buildings. It's that which makes these diffusers so versatile and as I said, very forgiving. So that's the basic difference between the American concept, if you like, and the European approach. So there are different types of high induction diffusers. There are ones that look like linears, there are swirls, obviously, there are also side blow solutions. And they all work in pretty much the same way. And that is by breaking the air up into a multitude of individual air streams. So instead of a four-way blow which clumps air together, we want to break it up. And the best way to imagine it is if you look at a swirl diffuser, even though it's called a swirl diffuser, the air doesn't swirl. The air from this vein goes in that direction, from that vein goes in that direction. It's breaking up the air into all of these individual air streams each one of which is highly inductive. And additionally, every vein over here that you're looking at, that visible surface, is actually a low pressure zone. And so you've got room air being sucked in radially along every vein and being thoroughly mixed in right at the face of the diffuser. And then we get that rapid temperature dilution and the room air being drawn in and the velocity being broken down. And the effect is very strong. You can see it in the smoke test coming up, but this is at a very low supply temperature. You get the rapid deceleration as the room air is drawn in. That smoke gets really thick because of the increase in the airflow rate, and the smoke thins out due to the dilution taking place. We have low velocities in the space. You can clearly see the individual air streams that I was talking about. This is a graph from an ASHRAE paper, and what it's showing is the two best performing diffusers from this test, which was for low temperature supply systems. And the swirl diffuser, you're seeing at the top here, the supply air temperature to the diffuser was 8 degrees, but if you look over here, this is a plot of the temperature measured 50 millimeters below the face of the diffuser as we go up 1 meter radius, 2 meters radius, so it's quite literally in the supply air stream. You can see at about 300 millimeters, the air temperature is 22.6, just over here, 22.6 degrees, even though the air to the diffuser is 8 degrees. And that shows you how incredibly high that induction really is, because that's just been diluted with room air, that's all it is. So I mentioned that we originally developed the what's now sold as the Harmony, but that was launched in 2005, 2006. Since then, we've developed the Fixed Helical Swirl Diffuser, which has substantially higher performance than that product over there. And what we were trying to do with this diffuser is to increase the maximum airflow rate, still keep it suitable for very big delta T's, which is not only important for low temperature VAV systems, but also for DX systems, which many of which operate with very low supply air temperatures. We wanted to keep the big, in fact, increase the variable air volume range, so to turn down to less than 30%, which is again not only important for VAV, but also for any application where you want a low airflow rate, let's say to keep noise down. You still want the product to give a stable air pattern. And this one can operate at a very, very low airflow rate or at a very high airflow rate. And the way we achieved that is instead of just having flat vanes, we've actually got vanes that have a twist in them, plus this cambered leading edge, and we've got a bell mouth as well, and then these very big trailing edges. And so this product is without a doubt the highest performing fixed vane swirl diffuser that there is. It has substantially higher airflow rate than the Harmony. The DN355, for example, can go up to 220 liters a second. The Harmony is limited to about 170, 180 in that region. 3 different neck sizes, but also the option of reducers, so that the diffuser can behave as if it were a smaller diffuser, even though they all look the same for architectural reasons. Or, of course, blanking segments for 2-way glow, 3-way glow, that sort of thing. Square and round face. The round face is for plasterboard ceilings or for freely suspended applications. The diffuser does not have to be in a ceiling. It will provide completely horizontal discharge, even if freely suspended. We are also coming under more and more pressure for low profile connection boxes. So we've just updated our selection tools, offering this. This is from a particular project in Sydney with 200 millimeters high, and that was the smoke test that you just saw of that new low profile box. So our selection tools are all on our website. You don't need passwords or anything like that to download them. They're just Excel based. And they all work on pretty much the same basis, which is the top left corner is key information, the right is optional information, and then we use white to guide you to the recommended solution. And so in this particular example, the DN355s have been chosen. The airflow rate's 120 liters a second. It's a system that's turning down to 25% from 120 at a delta T of -12, and the discharge height is 2.7. So here you can see it's blowing in all four directions. It's nearly 360 degrees if you prefer. And ADPI is 90%. I'll talk more about that in a moment. And so it's using white to guide you to the preferred solution. Now, ADPI is an important concept for us. I said beforehand that throw is not a function of velocity, and yet we are all accustomed to selecting diffusers based on throw to a terminal velocity of 0.25 meters a second, which is fine for normal products, but for high induction, it doesn't work because of that momentum issue. And so the question then is, well, how do we make our recommendations? And we've chosen a performance-based approach, whereby we're going for comfort. ASHRAE has a standard 113, which is called Air Diffusion Performance Index, and that is all about thermal comfort. In that standard, ASHRAE, or just in general, ASHRAE recommends that we should target an ADPI of 80% for good comfort. Now, what does that mean? Or how do they determine that? What they do in the tests is, if we did ADPI tests in this room, we would have a stand, and there are 4 different positions on that stand, 4 different heights, where we're measuring temperature and velocity. And that stand is then moved around the space. One does simultaneous tests all over the space, effectively creating a temperature and velocity matrix, if you like, in the space. And the logic is that if the temperature, let's say this point over here, is colder than the average, then there's a potential draft rate. If the velocity at the same point is quite high, well, then there's a greater draft rate. And those 2 factors are added together, and that point either passes or fails a formula. Similarly, if the temperature is higher than average and or the velocity is very low, then again, they're added together and that point can fail due to stagnation. And so 80% ADPI would mean that of 100 points, up to 20 are allowed to fail, either due to draft or stagnation. And obviously at least 80 have to pass. So you'll see our standard is in fact 90% ADPI. So we go better than what ASHRAE recommends for good comfort, but that can be changed if you wish. And so based on that, we can determine both minimum and maximum recommended centerline distances between diffusers. The minimum being how close can they go when the diffuser's at its full airflow rate, in this case 120 liters a second. How close can we go and prevent draft? And the maximum is how far apart can we go and prevent stagnation when the diffuser is fully turned down. And obviously you halve those values if it's to a wall or something like that. So it's quite easy to use. We also do have the options over here for closed ceiling, which is the diffusers in the ceiling, versus freely suspended. And you can also put in low-level return, which just helps heating. So in other words, 50% low-level return would mean that you've got 50% in the ceiling and then 50% from down here, which will obviously help draw the heat down and improve heating. So that's the basis of that selection tool. Just some photographs. And then more recently, you'll see that this is clearly based on the same diffuser, but it's a new product that we've just launched. It's called the Multiswirl, and it was done for the BBC in Wales. And normally, if one looks at something like that, you'd say, well, that's not going to work. I mean, we've brought these diffusers closer and closer together. Surely the air streams must be clashing and creating a draft. If you look at the smoke test, you can see the air's not going down. It's actually staying up. And the reason is that, yes, in reality, if I've got 2 diffusers and I bring them closer and closer together, yes, the air is going to start clashing. Yes, the air is going to be projected down and eventually create a draft. But if I get close enough, if I get really, really close, and they're high induction diffusers, the air that's projected down is sucked straight back up again. And so that's what we're doing with this diffuser. And so what one can do is you can put a whole lot of these end on end and effectively create a long row of these diffusers running through the space, very much as if it were a linear diffuser, but a very big linear diffuser, handling higher airflow rates than you could have with a linear diffuser, and yet you won't have any draft. So that's the new Multiswirl. These are tests at LTG on the acoustic side, but obviously it was the BBC with the radio studios and that had to be very quiet. In terms of heating, I mentioned that low-level return obviously improves heating, but we seldom are able to do that. And of course, the higher the discharge height, the more difficult it gets to heat. And we get to a point where eventually we really do have to project the warm air downwards. But if the heating load, or if the mechanical part stops heating, or if we actually start cooling, we need to alter the discharge direction to a true horizontal pattern to ensure that we don't create draft. And it makes a very, very big difference. So here you see some tests just from 6 meters height, nothing extreme. 2 identical tests, one with horizontal discharge and the other one with vertical. And it changed the warm-up time from 2.5 hours just to 25 minutes. But the other thing that's important is, even if I've got vertical discharge, how far down does the heat penetrate? If it penetrates to above the occupied space, then it takes a lot longer to warm up than if we get it to come all the way down to the floor. So these are two identical tests. The only difference is with this, with the second test, it was half the number of diffusers, so twice the airflow rate per diffuser, getting the air to project all the way down to floor level. Whereas with the first one, the air stopped above the occupied space. And clearly, it makes a huge difference. But it's only possible to project the air down into the occupied space if you're not going to create a draft. It's no good agitating the cold air and getting the warm air to where the people are if it's going to be hot and gusty under the diffuser. And so when we developed our helical range of swirl diffusers, of course we wanted an adjustable version, which is what this one is, but it was important to us that it is a high induction diffuser, not only with when it gives horizontal discharge, but also high induction when it gives vertical discharge, so that it would not be hot and gusty under the diffuser, and so that we could project the air all the way down to floor level when heating. The other thing that was important to us, and this is why I've got these great big X's over here, is that we wanted it to be a constant pressure diffuser. A diffuser that has effectively the same pressure drop when it's discharging horizontally as it has when it's discharging vertically, so that the pressure balance of your system isn't affected just because diffusers are motorized or have thermal elements. And if you look at these diffusers, this is the Trox diffuser, it's quite obvious that that one has a very much lower pressure drop, and that's in vertical mode, versus the same diffuser in horizontal mode. Or the same applies to diffusers where you alter the pitch of the blades, vertical for heating, 30 degrees for horizontal discharge. Well, clearly the pressure drop over here is going to be very high. And one project I worked on had this type of diffuser, and I recall very clearly at the nominated airflow rate in cooling mode, the pressure drop was 110 pascals. In heating mode, at the same airflow rate, it was 8 pascals. Well, that's obviously ridiculous. And so we were adamant that we wanted a substantially constant pressure drop. And we have achieved it. So this is the real product here, the adjustable helical swirl. It's a patented diffuser, and it's got a guide ring that moves up and down, and it's got adjustable guide vanes at the back that also move, and changes in pressure drop from the one side are cancelled out by opposite changes on the other side, and so we maintain a substantially constant pressure drop. You'll see it's also a very low profile diffuser, which means that when you've got restricted ceiling void heights, it helps one out on that side, and its pressure drop in general is very low, which means generally speaking we can put in a smaller neck size than the competitors for the same airflow rate. Like the fixed helical swirl, it's got the helical twist and quite a complex vane shape. And you'll see it is available with a reducer. Here the guide ring is slightly smaller than over there, where it's without a reducer, and that's why all of these are mentioned twice. From a neck size of 250, which is what that one was that I showed you, all the way up to a neck size of 1000. And the DN1000 is the largest commercially available swirl diffuser in the world. So this should be able to cover most of the airflow rates that you're likely to encounter. The diffuser is adjustable either manually via a thermal element or electrically. The larger ones are only electrical at this stage, but certainly the smaller ones, the most commonly used ones, have the thermal option. And this is the real thermal element over here. It simply screws into the back of the diffuser. You can see the thermal element over there. So no wiring is required, no electricity of any nature. It's just this, and then the thermal wax in there expands when it gets hot and changes the discharge direction downwards from from the diffuser. It's also manually adjustable, the bias, to get it more strongly downwards or more upwards if one so wishes, and depending on the discharge height. We've had to do a lot of smoke tests with the diffuser to get to properly catalogue its performance, its heating performance. And then this is one of the tests in Germany. So it's the DN500 operating at 650 litres a second in this example at a delta T of 7.5. And the smoke ultimately comes down to this level, which is 6.3 metres. In other words, what we're saying is the diffuser shouldn't be more than 6.3 metres above the floor if you're heating at that delta T. And we've had to do tests like this for all the different airflow rates, all the different delta T's, and for all the different neck sizes. So it's a lot of testing. But you can clearly see how the air gets really broad. It's because of the high induction, all the room air being drawn in, the velocity is broken down, temperature largely equalizes. So if somebody walks along here, they're not going to feel that at all. They will not know if they're under that diffuser. Again, we've got a selection tool, of course, for it. Again, using color to guide you to the answer. And the bottom row gives the thermal element setting. That's this setting over here, on here, depending on what the inputs have been above. So this can be factory set or just set on site before the diffuser is installed. Comfort can be put in and changed at the top. And we've got a little comfort guide over here, because if it's a transient space, for example, lobby or something like that, then there's no need to go for 90% ADPI. 70% would be good enough. Just a couple of photographs of them in various applications. Note this is an auditorium, obviously a very quiet application. The diffuser is a very quiet diffuser. It's stable at very low airflow rates, and so it's absolutely suitable for this sort of application. Also in Scotland, the new V&A Museum. But the adjustable helical swirl has limits. You saw over there, just at that example, 650 litres a second, delta T of 7.5, and we said, okay, maximum recommended height in that case would be 6.3 metres. Well, what if you are going to have twice that height? Then what are you going to do? How are you going to heat? Well, there's the solution, because this diffuser has been designed to handle exactly twice the height of what the adjustable helical swirl does at the same delta T and same airflow rate. So it's a new product, the Jet Swirl. At this stage, it's only available with an electric actuator, no thermal element yet. And it's only available in two neck sizes, DN400 and DN630. We do plan to bring out a DN710 as well. But it's the right product for a sports arena or anything along those lines. So there you see it again. So in excess of 20 meters. Very often though, the architects, as much as I like swirl diffusers, the architects aren't quite as enthusiastic about them. They would prefer to see nothing, or they will tolerate zones where recesses, perhaps for services, lights and that sort of thing, and they want to somehow squeeze the air diffusion in there as well, but it mustn't be seen. And that was the case over here. This is the Opera House again, the Western Foyer. And so what we did is we do have a solution for that. A diffuser that looks like a linear diffuser, but is in fact a high induction diffuser, and therefore actually can be recessed. It doesn't need coanda effect attachment to a ceiling. We can actually discharge diagonally and break down the velocity so as not to blow cold air down people's necks. And the way the diffuser works is by having these alternating streams, different jets of air, again breaking up the air into a multitude of individual air streams, as I said before, and they are manually adjustable. Over here we've got these vanes. It's this vane over here that I'm moving right over here. I can move it to a vertical setting or to a number of different positions. Simply, you can hear it clicking over there just by moving these. And so of course we can do one-way blow, two-way blow, more steeply, horizontally, or anywhere in between. The diffuser can be put together in, to create continuous lengths, or of course individual lengths. You can have supply and return, passive return, or a connection box right next to it, all in the same run. And if you do that, in order to prevent short circuiting between the supply and the return, we are able to simply close off the diffuser and do this over here, like that. So there I've just closed off that element. Air can't get out, so supply could be here, return over there. This element is closed to prevent short circuiting. In cooling mode, this is just a smoke test in the lab in Sydney. No sealing, and yet we've got completely horizontal discharge, and you can clearly see the alternating left, right, left, right, left, right, breaking up the air. Or the same diffuser set to heating mode, or to vertical mode, I should say. Again, you can see the crisscross, the high induction as the two air streams pass one another and draw in the room air to then create a really broad air stream that then moves down. So something that's not available yet, but that we're working on, is a thermal element variant of this for lobbies and that sort of thing. But unfortunately, it's not available yet, but will be coming. Again, we do have a selection tool for it, but working on the same basis as before, with white guiding you to the solution. It is important to realize that even though this looks like a linear diffuser, it's not a standard linear diffuser. This is a very high induction diffuser. It provides extremely high levels of comfort. But unfortunately, as I said, we at this stage cannot automate the discharge direction. So here again, there's the Opera House. And what this is showing is that this is a curved wall. You can see it on the outside. This is overlooking Sydney Harbour, and you can clearly see that curved facade. And so here's the diffuser over here. So for the first time ever, we've actually created a curved version of this. But we're not able to do it if we've got a flange. The flange, unfortunately, just crinkles. But we've got a flangeless version of this as well, and we are able to curve that. So if you've got projects involving a curve, as long as it's not a tight radius curve, then it is something that we are able to do as we've done over here. Now, the same concept of high induction can, of course, be used for side blow diffusers as well. And the perforated multistream diffuser is an example of that, where we are, again, breaking up the air into a multitude of individual air streams. And we do that through these hexagonal elements in the back. You can see it over here, hidden behind the perf. The holes always line up with the holes in the perf over here. But there are different types of elements with these little jet clusters, and they all have different directions. But they are adjustable through the face of the diffuser. So you can take an Allen key and put it into the center of that little hexagon, and you'll see that the direction of the Allen key is the same as the discharge from that element, the jet, as it were. So you intuitively know which way the air is going to come out of that. If you then push the Allen key back, that element moves back. You can rotate it to any one of 6 positions and release it. So it's fully adjustable through the face of the diffuser to increase the spread, reduce the throw, increase the throw, left, right, whatever it is you want to do. But as I said at the beginning, the reality is that high induction diffusers are suitable for short and for long throws. And so in reality, these diffusers are very seldom set. If you have a super short throw or you have a super long throw, then yes, of course, they can be set, and that can be done in the factory, and our selection tool will also say set it to long throw or set it to short throw. But generally speaking, the medium throw is good for most applications. Here's a smoke test of the diffuser. So first thing you'll note is a really broad air pattern. It's not a concentrated jet of air that shoots across and ricochets off the far wall, or limply just detaches off the ceiling and just goes flop into the space. Instead, we get good spread, and then the air moves across and then gradually filters down into the space. You'll see it from the side in the moment as well. So it's not shooting across and ricocheting, or just limply flopping down. Instead, the smoke is peeling off across the entire length of throw of the diffuser. And so this truly is a high induction, high comfort diffuser, and very good for draft sensitive spaces, restaurants, aged care facilities. They're going into a lot of education facilities in Australia now, hotels obviously, and so forth. Just a couple of examples of them. So this is them up here in the LinkedIn offices in Sydney, or in Sofitel in Christchurch, the Crown Plaza, all the bedrooms have them as well. This is in Adelaide. In school, as I said, there are a lot of education facilities that are getting these now. And there's the selection tool. The diffuser is available in 600 width, 950 normally, and 1500. So that would be the neck width, roughly. And 4 different heights. We've got what we call 1 row, 2 row, 3 row, and 4 row. So 1 row turn this around. 1 row would be just 1 hexagonal element. 2 rows would include the second one, which is offset. 3 would come down here to the 3rd one, and the 4th one would be down there. So it is, in that sense, slightly restrictive in that one is, the rows increase based on the hexagonal size. So one does have to work within those parameters. And here you can see the short, medium, long throw and white guiding one to the solution. We can do custom lengths. So there is, on this selection tool, there's a custom worksheet where we can do different dimensions to suit your project. But obviously those aren't stock items. We do nozzles as well, and to be frank, there's nothing really different about our nozzles to anyone else's nozzles. We have the option of swirl elements, of thermal elements to adjust, or the electric motors to adjust, different sizes. So that's all fairly standard stuff. In terms of nozzles, we do have a selection tool to give you the throw and so forth. But there is something that we do which is different, which we offer as an option. It's not an actual product in our brochure because it's a bespoke solution, but we've done it quite a lot. And that is what we call a nozzle cassette. You can see it over here. This is in Sydney, Darling Harbour over here, the new convention centre in the background. And this is a whole series of convention halls varying in width from 15 metres to 20 metres. Very high heat loads. For whatever reason, it wasn't possible to have ceiling swirls, so all the air diffusion had to be from one side. And you can see these nozzles are very tightly spaced over here, quite tightly packed. And yet, this is showing half the number of nozzles that was originally meant to go in here. Had the number of nozzles been doubled, I don't quite know how they would have fitted in, but even if they had fitted in, it would not have been possible to get comfort in the space. It just would not have been possible. So what we did is we offered nozzle cassettes. What the nozzle cassette is surrounding each nozzle is a multi-layered perforation that has air oozing out of it. The same amount of air comes out of the surrounding surface as goes through the nozzle. The difference, though, is the nozzle has a high velocity jet, whereas the air oozing around the outside, of course, is coming out very, very slowly. And so its momentum does not add to the air motion. So we've effectively halved the energy that would have created excessive air motion in the space over here. As that air oozes out, it doesn't just flop down into the space, but the central jet induces that surrounding air so that you get a combined air stream coming out of each nozzle, or surrounding each nozzle, as it were, and the length of throw and the direction of that combined air stream is determined by the central jet. What we also did is we've alternated in this one swirl and non-swirl, swirl and non-swirl, so we've got some longer throw and some shorter throw, so that you don't have all of the air coming down at the same spot. And then we've also, we can't make it up, I don't think, I can just see it over here on the underside of the bulkhead. We've got high induction, 2-slot high induction of these, discharging diagonally downwards, countering the strong clockwise air circulation pattern that is otherwise being created. Just doing everything to prevent excessive air motion from forming. We do this a lot for stages, so in theatres. It's always difficult to find space to blow air to stage areas. They obviously aren't normally round, I'll be frank. It's the only time we've ever done round, and we won't do it again. It was very difficult from a manufacturing point of view. But the concept is one that is worth bearing in mind because it does help with many problems. This is just a photograph from Germany. So LTG, as I said, is our partner over there. And there you can see the perforated multistream, the adjustable helical, our nozzle, four swirls, etc. And the reason I like this photograph is because in 1995 and then later on in 2001, we brought German air diffusion technology to this part of the world. Whereas over here, we're now seeing our air diffusion technology being taken to Germany, which I am particularly proud of. And that brings me to the end of the presentation, the end of the mixed flow side at any rate. So thank you very much, and if you've got any questions, please let me know.
So is there a minimum height for blowing down?
Is it minimum height you mean for all of the diffusers in general? Are you talking about?
Yeah, why not?
Okay, so all of the selection tools do give minimum height. So even the horizontal discharge swirls like that one, the bigger the diffuser, the greater the risk that there'll be a draft. So the minimum recommended heights are in the selection tools. For the adjustable discharge direction diffusers, it's generally speaking, people would use those from 4 meters up. But I would say there are times that even, especially if it's a perimeter zone with lots of infiltration and so forth, that you should already use the adjustable one at less than 4 meters. It just depends on the application.